Okay, so section 6.5 is called properties of logarithms. Most people, when they first encounter this, are just a little bit uncomfortable because they're not quite sure what to do. But once they've done one or two, my experience has been as a teacher, it doesn't happen very often for me, so I remember it. It's kind of it's an interesting puzzle that gives it a little bit of an academic challenge to you, but it's completely accessible. People like it. They think it's fun. Even if they can't find any good reason why they should know it or apply it, and there are reasons, good reasons, but they just find the idea of it and doing it kind of fun. So we're going to work on that. See if we can make it fun for you. We're going to go back to this idea up here that says if you've got the log base b of y equals x, that is exactly the same thing. This is the most important thing you'll learn in this chapter. It's the most important thing you learn about surviving any chapter on logarithms, is being able to go from here to here. And backwards. That's the reason I've got arrows on both ends of that. Y'all recall that? How many of you have it memorized? You get it memorized solid, and I mean solid before test time. You've got to be able to go from a logarithm to an exponent, from an exponent to a logarithm. Whatever form you've got it in, you've got to be able to convert to the other without a cheat sheet and with confidence, or you're going to be dead in the water on this test, guaranteed. Anyway, I want to talk about this relationship right now. I haven't told you why this is true. I could explain it if you wanted to, why it works out. However, I'm just, right now, I'm going to go on the idea that we accept this. People have been using it for thousands of years. It's been working great. We build bridges and everything with it, so probably it's true. But what I want you to notice is this. I'm going to change a color on something here. That's x. This is exactly the same x because they are equivalent expressions. In this one over here, what's the term we use for x? What is this thing? An exponent. Isn't this an exponent?
Yeah.
It's exactly the same x right here. Different form of that expression, but it's an equivalent form. This is an exponent. We don't usually like to see it that way because we're used to exponents sitting up above something in tiny form, a superscript. This is not in superscript place, but if you believe that that's equal to this, and you better, then this thing right here is an exponent, which means that logs are exponents. Logarithms are exponents. You want to know what the exponent is on this? You change it to a log and you evaluate the log, and it'll tell you what the exponent on that is. Let me drive this home just a little bit more. Logarithms were generated and worked on and thought about and studied, and tables, big huge tables were generated in the old days before calculators came along to answer very specifically questions like this. 10 to the x, no, other way around. Got that wrong. Let me write it the other way. It's got a 10 in it, but 3 to the what is 10. That's why logarithms were invented, was to be able to answer this, because you cannot get at that x. You can't get at this exponent algebraically. You can't isolate x by adding something to both sides, or dividing something to both sides, or multiplying something by both sides. You can't get at that x algebraically. That's why this is called a transcendental. It transcends the algebra function. And yet people in the projects and things they were doing had a need to find out what that x was. Not approximately, but to any degree of accuracy that was necessary. 6 decimals, 8 decimals, depending on the project, sometimes accuracy was really important. And you can look at this and say, well, I know it's got to be at least 2. Can you see why it has to be at least 2? But it can't be 3. And it's way closer to 2 than 3, because this number is way closer to 9 than 27. Still bigger than 3, still bigger than 9, but not by much. So this thing's got to be a little bigger than 2, but not by much. That wasn't good enough. People needed to know what that actual number was in order to do different things with the math and the engineering that they were doing. And so logarithms were invented, and I'm not going to go through that process because that's a long historical thing, but I want you to see how important things were. This is a very, very old book. It was in a pile of books that were scheduled to be taken to the dump. I went through it and found a whole bunch of really cool math books that nobody uses anymore. But I want you to see this. It's just people that used to walk around college campuses in the 1950s and 60s who walked around with this. If they were studying engineering or math, they walked around with one of these and one of these. Now you guys probably don't even know this is what this thing is. I had to buy this off of eBay too. Nobody buys these anymore. This used to have, I mean, it's busted, it was a leather case. This used to have a little thing that you could attach to your belt. You'd always know the engineers and mathematicians because they had these things clicking like a pistol on the side of the pants all the way across campus. They always had one of these in their packs too. You had to buy it at the bookstore. This thing is a slide rule before calculators. It's very, very well designed. There's a hairline thin line on this thing, and there's things on both sides. And the reason it's called the slide rule is because this middle thing slid around. And you had to line up these little hairline things. You had to have good vision. And then you put this over at a certain place like this. I don't know how these things operate. I have to study it. You get it just to the right place, and it would give you things like logarithms, accurate, and sine, cosine curves. Those are transcendentals too. If you know how to operate this thing, you could get values accurate to about 4 places. To the nearest 10,000. If you know how to operate it. It's really cool. Until a few years ago, in Mr. Ridgeon's room, there was a great big one of these hanging up in the classroom. It was used for teaching in the old days. It was brought over from the old high school. I mean, this school was built in 1990, I think. In 1990, and we were using calculators by then, maybe not graphers, but we had scientific calculators, so there was no need for these, and yet they hauled that thing over from the junior high, which was the old high school, over to here and put it in Mrs. Beautiful's room. She was a teacher that was here for retired since, and she used to teach with it a little bit. She was really old, older than me. Anyway, this book that you would get, you'd have to find it at the top. People were really good at using it. You can see this thing's been used by somebody's thumb a lot, because you have to flip through and you go, which table do I want? Look at these tables. You flip through there. This one is for values of trigonometric functions of 17 degrees. Angles of 17 degrees. This whole page. Over here, we've got instructions for using auxiliary S&T tables. This is logarithms of trig functions. Ooh, transcendental or transcendental. That's the tables for that. This one back here is logarithms of trig functions more, cubes and cube roots. You can look those up. Exponential and hyperbolic functions. Don't even know what those are. But these were tables which gave values. And people used to have to take these things and look them up. In the old days, even when I was in school, they would hand out a textbook. This much of the back of it was tables. Because we didn't have, a lot of kids were not able to afford calculators. I mean, it was kind of like this. A lot of people don't have graphing calculators. We provide them for you. But as you know, some of them bust down. They break down and no good. That was kind of the situation it was with just regular old scientific calculators. Some kids couldn't afford them and the school didn't provide them. And so the back of the book provided tables. You could look things up. So things have come a long ways. You should be extra grateful for those little tools on your desk because they are powerful. Very powerful things. You don't have to have this junk anymore. It wasn't junk at the time. It is now. It's become obsolete. Anyway, that's really neither here nor there. And I'm sorry those people, all you got to do was listen to them. But they were invented to answer questions like this. So what I'm trying to get at here is that when you have an expression like this and you want to know what this thingy is, you got to log it. And if you're looking for an exponent, you got to understand that the log that you're using is an exponent. And so the log, which is an exponent, ought to behave like exponents when we add and subtract, multiply, and divide them. They have to behave like exponents. And you go, all right, I'll buy that. That's an exponent, so it ought to behave like an exponent. But how do exponents behave? Well, you just need a reminder. This is how exponents behave. If you have x to the m times x to the n, what do we get?
X to the n plus n.
Yeah, because ultimately we're trying to multiply, and so we come down one on order of operations to remind us what to do with these. Remember that little thing I showed you? Okay, so if I have x to the m over x to the n, we get x to the m minus n. And if we have x to the m raised to the n, you get x to the mn. Okay, and if you have the nth root of x to the m, you get x to the m over n. So, if what you're trying to do is multiply two things with an exponent, you add the little guys. In other words, products. in a general way, I mean, this is not really mathematical talk, but I think it'll, you understand what I'm saying. Products, that's what a product is. You remember product means times? Products become sums. Quotients become differences. Powers become products. And roots become quotients. Everything's a step down, order of operations, whatever it is you're trying to do. This is how exponents behave. So that is how logarithms ought to behave. We're only going to deal with these three. And it looks like this. This one right here, the first one translates over like this. If you have the log, one log, I'm just going to leave this base 10. I'm not interested in the base at this point. Well, just so you understand, it's not just base 10. I guess I'll just call it b. We don't care what it is, but it's a log base b of m times n. That's your product part right there. And I know you're going, that isn't what that looks like. I mean, this was, yes, logs are exponents. Logs are exponents. And I've got the log of a product. So it becomes the sum of two logs. Products become sums of logs because logs are exponents, and it became the sum of exponents. Now I've got information right here. I probably couldn't do it without looking at my paper, but I can prove these to you if you're interested in seeing it. If you want to see it, I can show you why this actually comes out to be true mathematically, if you'd like. Quotients, like this, the log of a quotient. Exponenting, I mean, this is an exponent. Quotient becomes a difference of logs. If you have one log of a quotient, it becomes the difference of two logs. Because logs are exponents, they behave like exponents, became the subtraction of exponents. You see what's going on? How they're behaving this similar way? Okay. This one's a little weird. This one says the log base b of m raised to the n. That becomes, this one's a little touchy, so we might want to pay attention. If you're still writing, finish writing and watch up here. This is the one that's a little bit bizarre, a little bit strange to at first when you see it, but it's also the most important one. This is the most important for progressing in this chapter, this one. I need you to understand that this part of this expression, that's an exponent. We've agreed that logs are exponents, right? This part is also an exponent, more like what you're used to seeing. So what I have is an exponent to an exponent. That's what I have here, an exponent to an exponent. And it's supposed to become a product. So it looks like this. Now I'm going to write this down, and you think before you go, what? This one is equivalent to this. No, it doesn't distribute. This exponent is multiplied by this exponent because powers become products. So I'm multiplying this exponent, n, times this exponent, log base b of n. So this is the multiplier right there. There's your product right there. Most people don't remember this. If this is how I got through math, believe it or not. A lot of times I would look at that and go, yeah, that makes sense. And then when I would encounter it in an exercise, I'd go, I can't remember why that makes sense. But I knew it made sense to me once, so I'll go with it. That may be what happens here. This is what actually is going on that most people memorize. They look at that expression right there and they go, oh yeah, this guy gets to crawl down in front there. That's a rule. They don't remember why. They remember it was convincing at one point, but they just say, oh yeah, that gets to come down front. I remember that rule. This is kind of a weird one, but this is an exponent times an exponent, which is what happened here. You see, it's just that the first exponent was written as a log, and the second one is where it belongs, where you're used to seeing it. So it's a kind of a combination of the two at once, and it's kind of obscure. It's kind of weird to some people. But those are your three properties of logs. And now we're going to play with them. By the way, going from here, going from a single log to a bunch of other logs like this, going from this side to this side is called expanding the logarithms. If you have a situation like this where you got a whole bunch of sum and difference of a whole bunch of logs and you want to write it as a single logarithm, like this side going this direction, that's called condensing, putting them together. Okay, I hope you have these written down, because in order to stay on here and videotape this, I got to erase this in order to do some problems. You got this written down so you can reference it if you need to? Okay, it's also written for you in the core concept on page 328. It's a summary of what's going on, what I just showed you. I'm going to jump straight to example 2. I really don't like example 1 at all. It's become obscure. Well, it's not obscure. It's become obsolete by your calculator, so I'm not going to make you study that part. What we're going to do is we're going to practice expanding and condensing logarithms. We're going to practice writing one side, having one side and writing the other side. We're going to get this one, we're going to write this one. And I'm going to do a couple problems for you, and then I want you to try it. This is where it gets a little bit fun after you've gotten through the uncomfortableness of dealing with it for your first time. This is the deal. So if I'm just going to make this up, if I have the log, again, I'm going to let it be base 10 so that I don't have to keep writing down base b. Anyway, I'm going to say this one's base 10, and we're going to have 2x to the third cube root of y squared over z to the 7th w. That's quite a mess. I'm going to expand this for you. And this is one of those deals again, before you go, what? What the heck's she doing? I want you to study it, and I want you to let your eyes go back and forth between either what you wrote or what's in the book on these properties, and see if you can understand all at once. That's a huge expansion, by the way. That's a disaster expansion. But you could do it if you think about it for a minute. You could probably do this as soon as you see how this one results. So it's going to be the log of 2 plus 3 log of x plus 2/3 log of y minus, and for the first time I'm going to use parentheses, but after this you won't need parentheses, I'll show you, minus 7 log of z plus log w. What's that? Think about it. Let your eyes go from one thing to the next and think about it for a minute before you say, now what? I'll explain it better in a minute, but you think about it and see if you can understand why that expands that way.
That actually makes sense. Yeah, you know.
Yeah, that thing's disastrously monstrous. You won't have anything. This is your very first example that I'm giving you. You won't have anything that hard on your exercises. And if you understand that, you're going to be great. This is the first of all, notice that I've got a product here and there. Those all turned into plus signs when you write another log. So it's a log of 2, that's your first one, plus, because it's a product. And this is x to the third, so the exponent comes around front, using that other property. 3 log of x, this is actually y to the 2/3, so the 2/3 comes around front. See it? That was an exponent of 2/3, and it comes around front because of the third property that we learned. Then minus. Why minus? Because we're now going to the bottom of this is the quotient. That's the minus sign right there. It's the quotient of a product. And it's going to be z to the 7th, that 7 comes around front, and that w doesn't have one. But because this is a times, this is a plus, log w. No exponent in front, because there wasn't one. It's a 1. You follow that?
Yeah.
Now I want to do one more thing and show you that this will be the case from now on. You don't have to write this in parentheses. If I distribute that negative, I get that and this. Right? Okay, moral of this story is, if you understand that distribution right there, if it's in the denominator, it has a negative sign on it.
What if it's negative in the denominator?
Then it has a plus sign.
So I thought.
But it won't have a negative in the denominator. If this fraction right here is negative, that'll be right here, and then you do this. Because it belongs to everything, the entire expansion, okay? But I don't think you're going to run into that with your first experience here on the exercises you have to do, because they're not trying to beat you to death with it. I am. I'm trying to beat you to death with it. I mean, and if you understood this, you're going to be fine. You don't have to put in parentheses back here if you understand that if it's in the denominator, a negative will be distributed through it. So everything that's in the denominator, whatever creates a term from the denominator will be a negative one. Follow that? Want to try one?
Sure.
Okay, you guys try this one. Try expanding this log. Log of ooh, this one will be good. Let's see if you guys can handle this. It's going to be, I'm going to call it 8 x to the, I'll just say x. 4th root of z cubed p over y to the -3, this will be a fun one. -3 r to the 1/2. Give it a try. I'll come around and help you if you're stuck on something. Let me know. See if you can deal with that negative sign in the denominator. That's kind of what you were talking about, Connor. Was it you that asked what if it's negative? No, you did. This is kind of like what you were asking. If you're struggling, let me know. I'll come around and help. This will be difficult to do without a piece of paper. Ready for me to write the answer?
Yes.
Some of you are. Kind of run out of space, huh? With expansions or lengthy, especially when you have a lot of things to deal with. You don't need that negative around to everything.
This is what makes sense. That's what we say. This is what we mean.
Next time.
Yeah.
We'll take that line. You know what I mean? I would think about that as being a positive. Because remember, when we talk about products and quotients, we can move negative exponents where they're not, and they'll become positive. Okay, we ready for the answer? Don't panic, because I doubt very many of you got this first one, if anyone at all. The first part of this expansion is 3 log 2.
Wow. Not even close.
Because that is 2 cubed.
I'll let you do log 8 or no.
I know. And I didn't expect you to get it, and it's okay that you didn't, but do you understand why this one, log 8, is actually written 3 log 2? Because 8 is 2 to the 3rd.
Yeah, couldn't you just say log 8?
Because the objective here is to expand it, well, is to make it as simple as possible. Any exponents that occur, whether they are obvious or not, should be brought around front so that this thing that we're logging is as small as possible. It's kind of like a simplification of a fraction. Okay? And that's okay that you didn't pick it up. But maybe now that you've seen it, you'll pick it up next time. You want to look at these numbers. See, that one was just 2, which is a prime number. There's no exponent on that, but there is on this. If this were a 7, you'd be okay. If this were 15, it would be okay. It's not a perfect square or a perfect cube. But if this number is a square cube or 4th power or something like that, you're going to want to split it up exponent-wise. So that first term is like that. Don't panic, then don't be mad if you miss that one. It's okay. Then plus, I'm going to the x next, It has no exponent on it, so it's going to be log x. This one is z to the 3/4. It's also in the numerator, so it's going to be plus, and the 3/4 comes down here, log z, and plus log p. And then I'm going to do something that I think will save you as far as having to deal with negatives. I'm also going to put this in the numerator. That's going to be plus 3 log y. Because this negative 3 right here, because it's a negative exponent, can be put up here, and there's really a y cubed up here, and this isn't here. You see what I'm saying?
Yeah.
And then it will be minus, there's only one thing in the denominator now, minus 1/2 log r. Now, I can do this for you again and show you that you can still deal with it if you leave it down here. Do you want to or not?
I did it without putting it up.
Do you understand that either way, whether you move this before you expand it or whether you expand it with the negative on it, it's going to turn out to be a positive 3 log y? Because you'll have a negative, negative, negative because it's in the denominator, negative because the 3's coming down front. You see what's happening? So either way you handle it, it's going to turn out the same way if you don't make a mistake. I prefer to adjust all of this so that all my exponents are positive before I begin expanding. Sometimes I've even preferred to write it like this. I completely rewrite this as 2 to the 3rd x z to the 3/4 p y to the 3rd over r to the 1/2 before I begin. I make those changes so I can see what I'm dealing with here without having to make the changes in my head as I encounter it. You know what I'm saying?
Yeah.
All right. Now we're going to condense a couple together. We're going to start out with something like that, see if we can rewrite it as a single log. That'll be fun.
We will see.
Okay, so here's an expanded log. 4 log 2 plus 2/5 log x minus 7 log q plus 1/2 log z minus, oh, this will be a fun one. I'll try to see if you can handle this one. 5/2 log y minus 3 log p. See if you can condense it. And by the way, your answer will be like this. It will be log, and then you'll have a bunch of crap right here. It'll be 1 log. That's the idea. And condensing it is to condense it into a single logarithm. That's a very, very useful skill you'll see in a little while. Being able to condense a big, long string. Do you want me to complete this one and then give you one to do so you can kind of see how it goes?
Yeah.
Should we do that first?
No, I'm going to get it.
You want to try this? Okay, good. Try it. Give it a shot. And by the way, if radicals are necessary, I prefer radical form. So don't leave exponents as fractions, if they're fractions. Choking on your coffee, are you? Okay. You guys are getting really proficient at it. That's why you're finding this to be. So are you guys finding this sort of fun like I hoped you would? It's kind of interesting? No? Connor's shaking his head. I hate this crap.
This is math.
It's kind of a puzzle, but it's accessible, but it's a little bit challenging. It's kind of fun.
I like the other way better.
You like expanding better?
Yeah.
Well, condensing is going to be bread and butter when it comes to solving the log equation. So you're going to need to be able to do this. It may be that you like the other one better because this is your first experience with this and it's not as easy.
Well, actually, you might be right though, because you're probably right. Oh, the last problem she has.
Ask a neighbor, call me over, whatever it takes if you're struggling with
Because
something.
the next one's.
I deal with it.
So I think you're still talking about.
I'm so wrong.
Because they had switched, yeah, it was about 16, so I think that was it.
It's a negative thing, just stick it downstairs.
I think that this one is.
Well, you get 2 over 5.
So, you know how it's. Oh, yeah. I like
Just as she's typing you on.
Yep.
Is that how?
Pretty sure that goes up. Five. Oh, wait. Seriously, you want negative exponents?
No, I don't want it.
Don't want.
The answer should not have negative exponents, and it should have radicals instead of fractional exponents.
Can you bounce between?
Okay, I'm gonna write the answer here. Let's see if you got what I got. First number is, in the numerator is 16. You see that? Everybody got that one? Good. The next one's going to be the 5th root of x squared. Is that right?
Yeah. I would have gone.
I'm gonna jump over this one because, and this may not have occurred to you, but any term that's negative belongs in the denominator because of that distributed negative sign, remember? So I'm gonna jump over to here. This is gonna be the square root of z, and that's it.
They don't like to add things.
I don't talk about that. I don't talk about that.
Positive ones are in the numerator. Negative ones go downstairs. That's what we did when we distributed that negative. Anything that was negative ended up coming from the denominator, so we got to put it back in the denominator when we condense it. You see what's happening? Okay. So I'm ready to deal with the negatives now. That one right there is going to be q to the 7th in the denominator because it's a negative one. Are you with me there? Okay. I'm going to go ahead and deal with that negative p. It doesn't really matter the order because we're multiplying. So I'm going to say p to the 3rd. That's an easy one. But that one right there is going to be y squared root y.
I missed that one. I missed the last one.
I squared.
I threw a kink in things just like.
Oh, because you can. But wait, does it matter which order you write them in?
No, because multiplication is commutative.
Oh, yeah, take 2 y's out of it.
I just missed one. Let's go. I just missed the y squared.
Okay, this thing right here, if we go by in stages, is y to the 5 halves, right? That's the same thing as the square root of y to the 5th. There are 2 pairs of y's in there. Y comes out, another y comes out, and there's a y left.
Oh, yeah, because I got y to the 5th. You can take out 2.
Do you see how that turns out to be y squared root y?
Yeah.
Let me show you another cool thing about this. You know how bad I hate mixed numbers like 3 1/4? You know how bad I hate that?
Yeah.
This is one place where it can be useful. One place. What I can do, instead of going with the radical like that, which is fine. If that's how you like to see it, that's great. It's a great way to do it. But this is the same thing as y to the 2 1/2.
Oh, okay.
So I have 2 whole y's, if you will, and half of another.
That's obvious.
That's a way to think about it too. So if you end up with an improper fraction up here, it's a simplifiable radical, and you can do it with mixed numbers. This is the only time I find these useful in algebra, but they can be useful here. Okay. All right. So that's how that one expands. Now understand that this next one that I give you is also going to be, it's got a quirk in it. See if you can figure it out. I want you to condense this one. It's going to be 2 log 5 plus 4 log x minus 3 log z plus 5 log x minus or plus 6 log z minus 2 log y. Okay, see if you can condense that properly. think you've got it, check with your neighbor, and if you need some help, let me know.
You just put it underneath this y squared.
So what did you get less?
Yeah, that's all. That's what I was thinking.
Yeah, probably not. Well, I'll just really go ahead and say to do what?
Because there's 60 on the top.
Yeah.
I think
she's
Oh, okay, that makes sense. I just brought this out with that one. We'll see. As you-
Yeah.
Oh,
Yeah.
and either way, it would still count. Okay.
That's
Yeah, okay, because it's 2, 5.
That's it. That they actually behave like exponents. They do, because they are.
So, like, there's not like a fraction.
Yeah.
So it's just with
It's really not. What's the, you don't have.
No, that's fine.
No, she's saying like, when you yeah, you'd square it.
Which is like, first one, there's gonna be like 30. So,
Yeah, actually, yeah.
All right, I'm perceiving that a lot of conversation is drifting off of the math, so take a look at this.
Oh,
You guys were right here, but these guys were all. Okay, let me show you a couple ways to look at this and show you that they are the same and the logarithms really are exponents. Let me just show you here. If you just tackle this just like it is, then it would be the single log of, and it would be 25, x to the fourth, right? Then I'm gonna go pick up the other positive ones, x to the fifth, z to the sixth, and that's it for that. And then if I do the bottom ones, which is the negative ones, it would be z to the third and
Y squared.
y squared, yeah. And then you got a little cleanup to do, right? Okay, because this thing can be simplified. These can be combined and these can be canceled. So you end up with the log of 25, x to the ninth, z to the third over y squared. Is that right? Y'all see that? Now, let me show you another way to do this, another way to tackle it. Some of you probably discovered it, that it's either way. Before doing this, you could combine like terms.
Oh, Joe, look at that.
If you didn't see that, then maybe you see it now. And so seeing that, but when we get to here, we added that 4 and 5 to get that 9. Well, look, you got 4 logs of x here and 5 logs of x here. That's 9 of them by combining, because you added them here and we add them here because exponents are logarithms. You see what I'm saying? So instead of tackling it like this and reducing the fraction, which by the way is a perfectly great way to do it. I'm not trying to discourage that. I'm saying there's another way if you see it. And it brings home the idea that logs behave like exponents, and that is to look at your like terms. This is a log x term, and there's 4 of them. This is a log x term, and there's 5 of them. So we could combine them. I'm going to leave this. I'm going to write this way. I'm going to do this first simplification. Is that okay? And then I look at it and say, oh, I got 2 log x. Oh, and I got 9 of them all together if I collect log x. And then I got a 3 log z and a 6. I've got a negative 3 of these and 6 of those. That's 3 of them when I combine them. And now if you condense that result, you get exactly what we did as the end part of the other one, which is log 25 X to the 9th, Z to the 3rd over Y squared. So you can combine like terms first because combining like terms is the same thing as adding the exponents once you get two of them with the same base. Do you know what I'm saying? Either way is good, and I can follow them both, and when you show me your work on a test, it doesn't matter to me how you tackle it, whatever you like. But I just need you to understand there's two ways to handle it, because logs are exponents. They behave like that. Okay, you won't hit anything nearly this difficult. It's unfortunate. Your exercises are pretty rudimentary, pretty small, pretty quick, but you should be able to tackle them with confidence and do them quickly. I have two more things to show you. I know that's always okay. Let's go do this. Now there's two more concepts, two more things to do. One more concept, and then one more problem to look at. Okay. This one is a proof, and I'm not going to tell you where it's leading until you see it at the end. So just try to follow me, try to follow the algebra, and say to yourself from one step to the next, hopefully you'll be able to convince yourself, yeah, that seems reasonable. And if it doesn't seem reasonable, talk to me about it. Because this little thing right here is one of the most powerful things you have in your toolbox for handling logarithms. Consider this with me for just a minute. A to the x equals n. No numbers at all. Can you use, well, I'll go with the algebra on this. What you do to one side, you do to the other. That's one of the main premises of algebra. So if I were to log this side and log this side, and then apply that little principle that we had, it would be x log a equals log n. So this exponent became a product. You following that? Okay, yeah, I'll go with that. Maybe I'm right there. I think I am. Okay, so if in this case right here, I solve for x by dividing, because now this is a product, I can use algebra. I'm down to using algebra again by using these logs. That x became accessible when it came down around front, became a product. All I got to do is divide by log a to solve for x.
So then it would be just log n minus.
Does that make any sense to you?
Yeah.
You see that we started out with something that involved x that was inaccessible because it was up here. We could not get at it algebraically. So we used a transcendental logging. We logged both sides, applied the product property you learned today. And then x became accessible algebraically, and we solved for x. So that this expression right here and this expression right here are exactly the same. Right? Notice also this. Well, I think I am going to show you this. Take this very same expression again, a to the x equals n, and tell me, without logging both sides, that was an algebra move right there, and we're able to get at the x and solve for it. So forget this right here. Instead, very same expression, tackle that by changing that exponent to a logarithm, like you learned at the very first. Can anybody transform that thing into a logarithm?
Log base of a plus of n
equals x. Does that look familiar for those of you that have memorized this or are looking it up?
Yeah.
That expression and that one are exactly the same. Okay. Again, I'm going to change color on you so that you can focus on something. This x right here is exactly the same as this x right here because they both stemmed from the same expression. It's just that this was handled algebraically by logging both sides, and we got this. This one over here, we changed the exponent, the very same expression. We changed that to a logarithm. So that this green x and this green x are the same ones. Do you agree? Do you agree with that? Because they started from the same expression. It's two different ways to isolate the x. Since they are the same x, I have this by substitution, that the log base a of n is the same thing as the log of n over the log of a. Would you agree with that? Because they're both equal to x, they're equal to each other. Remember that from geometry, substitution? So this is one way to solve for x using the properties we learned today. Log both sides, bring the x down. Now it's accessible algebraically, we divide. Here's another way from the beginning of the chapter take an exponential, change it to a logarithm, that isolates the x also. Set the two equal to each other, and you have this. And you might think, okay, I'll buy that. And you might not think, okay, but what is that? It's the coolest thing in the world is what it is. This is called the change of base rule. And it is nearly as important to memorize as these two being equivalent. I would say it's right on this maybe same level with it. You need to know this. And the reason you need to know this is because there are several millions of logarithms out there of different bases. On your calculator, you have two. You have two buttons. You have log base 10 and log base E. Those are the only two buttons you have. And yet, quite often, things require you to have log base 3 of 4. Figure out what that is. And you don't have a log base 3 key. In many of your operating systems, if you go through and hunt through the catalog and figure things out, you can actually write it as log base 3 or something. If you want to figure that out, you can in your calculator. I'm not going to teach it to you because this will get you your result just as quickly. This is what I mean. If I want to evaluate the log base 3 of 4, like I just said a second ago, that's the same thing as the log base 10 of 4 over the log base 10 of 3. Now you can use your base 10 key. Because these are base 10s. See right here, look. This was log base A of n. Now this is log base 10 of n and log base 10 of a. Now you can access it with your log base 10 key. See what I'm saying? Now I need you to understand this as well. It doesn't matter which of the keys dedicated you use. This right here is exactly this log base A of n is also the natural log of n over the natural log of a. You check it out. It doesn't matter whether you use your common log key or your natural log key. You have them both. It doesn't matter which one you use. It will change it to the exact same. So up here, what I'm saying is this could also be found, the log base 3 of 4 could also be found by natural logging 4 and natural logging 3 and dividing them. You get the same result, whether it's common log or natural log. As it turns out, if you had the keys, you could even do this. Now, don't write this down. You could even do this. If you had the log base 3 of 4 and you wanted to figure that out, you could do the log base 19 of 4 divided by the log base 19 of 3 if you had a base 19 key. As long as the logs that you use on this side of this expression, as long as the logs you use over here have the same base, that way you changed it from log base 3 to log base 19. Up here you changed it from log base 3 to log base 10, which you have a key for. Here you change it from log base 3 to log base E, which you have a key for. So these two are the most important. But this is also true. Nobody would do this, but it's still true. As long as these have the same base, you can take the big guy, log it, the little guy, log it, find their quotient, and you've got the answer, the evaluation of it. So let's go back to the one we started with, this one right here. Can you find for me the value of 3? No, I don't want to do that. Never mind. Bad thought. Last thing. I want to talk to you about logarithmic scales. Not really scales. We do an awful lot of growing money, compounding continuously, and we grow bacterias, and we decay radioactive materials, all with E as the base for the exponent. But there are 3 huge, gigantic scales that are used routinely that are log base 10. One of them is the Richter scale reading for earthquake. One of them is the decibel reading for intensity of sound. And the other one is the pH scale for basicness and acidicness. It goes from 0 to 14, right? These are on log scales because the difference in the numbers is so completely, totally vast that we have to use exponents. We have to use scientific notation kind of like. Because, for example, the difference between a 4 earthquake and a 7 is actually 1,000 times more intensity. Because the Richter scale reading, when you hear a number on the news about an earthquake, it can vary so much in intensity that they can't actually talk with real numbers, because they would have to say, for example, this had an intensity of 1,000, whereas the one in California had an intensity of 100 million. Our brains don't handle the comparisons of those two very well. It's a lot easier to say 4 and 7. And what it really is if you have a Richter reading of 4, 10 to the 4th, that's what that means. That's what that 4 is when they tell you it's a 4. That's kind of simplistic. There's more to it than that, but that's what we're going to go with for right now. And if you have a 10, or you have a 7 Richter, by the way, have any of you ever experienced an earthquake?
Not a big one. Yeah, just a little.
Little one? And did you feel it?
Barely.
Yeah. Did it break anything? Did it make the building sway? You can only feel a swaying building if you're up in a really tall one, but they sway. They move around. It's really crazy. If anybody ever experienced one that's a 7? If you just barely felt one, by the time it got to you, it probably had a shakeability factor of 4 or 5. These don't break things. These sometimes, very seldom, but sometimes knock things off of shelves that they're pretty close to the edge. These give you a little bit of a scare. But these, 7 and bigger, starting at about 7, they break up highways, they topple buildings, they open giant chasms in the earth, they kill people. These kill people, these are barely felt. And yet the difference between 4 and 7 isn't much.
You tardy?
Yeah, I signed in, but she wasn't in there when I showed up, so.
Okay. Just my mistake. What about Sophia? Thanks.
Okay, so if it's the exponent, and it is, that's what we're discussing in this chapter. If it's the exponent that is the Richter reading, let's reduce that. What you end up doing here is this is 1, 0, 0, 0, 0. And this is 1, 1, 2, 3, 4, 5, 6, 7. If you cancel 10s out of this, you end up with, I missed one. That's supposed to be 1,000. What you end up with, what we're talking about here is that the difference between a 4 earthquake and a 7 is 1,000 times more intensity. That's why this one kills people and this one can barely be felt, because this is 1,000 times more energy. The difference between 4 and 7 isn't much. But when you understand that it is an exponential or a logarithmic scale, since logs are exponents, you see that the difference is in the exponents here is 1,000 times greater intensity. The same thing is true about your ears and the decibel scale. I'm not going to talk about the pH scale today. We'll do that in pre-calculus. But decibel scale, your ears are the most phenomenal instruments. They're amazing. They can hear. You can also tolerate without pain and without busting your eardrum things that are millions of times, trillions of times more intense than that, and your ears can hack it. There is a point where your ears drums will burst, and then we measure that with decibels, because the range of numbers involved, just like these, is just so vast that we put it on a log scale so we can talk about numbers in a sensible way. The thing for decibels, now we're going to get to the actual log of them. It's a little d and a capital B. Actually, they use the Greek letter beta if you're really saying it. So it's dB. This stands for decibels, and it is equal to 10 log base 10, which is understood, of the intensity of the sound, meaning the energy involved in the sound, over the minimum energy detectable by the human ear at 1 meter. This is times 10 to the negative 12. This is 1 over 1 with 12 zeros following it. That's how cool your ears are. At 1 meter away, you can still detect a sound with that minimal amount of energy. Little teeny tiny shakeability in the air. You can detect it if you're 1 meter away. You got good ears. Okay? This is the actual intensity of the sound. You take the quotient of it and you log it. That gives you it gives you a scale like the Richter scale. Now here's the really cool part, I think. This B right here stands for the B part of decibel, the bell part of decibel. And this D is for deci, decibel. Deci means 10. That's the deci right there. Bell is for Alexander Graham. He's the scientist of sound, like Edison is the scientist of electricity. This is a decibel. He got the name because it was studying sound. Okay? When the decibel reading gets to be about 120, you'll generally burst your eardrums, and that's about the sound, that's about the intensity of sound of a jet engine if you're not very far away from it. The interesting thing is, if you were standing behind a jet engine and you could withstand the heat coming out of there and the wind that would blow you to the ground and crush your head, if you could withstand that, you wouldn't hear anything. Because the force coming out of that jet engine is, it pushes the air out of the way. And that's how sound's transmitted, through the air, with transverse wave, right? If there's no air, there's no transmission. You can't, I love the thing for the aliens, when Alien first came out, it said in space, no one can hear you scream. It's true. They can't. There's no air to transmit a scream or sound of any kind. So when you on Star Wars, when you see ships blow up and it has this huge concussive, that doesn't happen. There's no sound. All it is all light. Anyway, so it's kind of ironic that a jet engine will blow your eardrum up if you could hear it, but you can't because there's no air to transmit it. Besides that, you're dead from the heat. So. Okay. Now, really quickly, I gotta get past this last one. I get talking too long. Here we go. Listen up. Shh. For a sound with intensity I in watts per square meter, you don't have to understand the units. The loudness L, they're calling it L of I. They're calling this decibel, they're calling it the loudness as a function of the intensity. That's how you pronounce that. A loudness as the function of the intensity is this 10 log I over I naught. And by the way, I naught for all of your purposes is going to be 10 to the negative 12. That's for normal hearing people. So that I naught has a value. And it tells you that in this, but you might want to remember it when you have to do it. An artist in a recording studio turns up the volume of a track so that the intensity of the sound doubles. The question is, how many decibels greater is that? It's not to double. You do not double the decimal because decibels are a log scale. So if you double the intensity, you do not double the decibels. If you are sitting at 40 decibels and you double the intensity, it does not go to 80. As a matter of fact, it doesn't go up by much at all because it's a huge logarithmic scale. So here's how we're going to investigate this. It wants to know by how many decibels did it go up. Does it make sense to you that it went up by this amount? L of 2I, that's your doubling intensity. Minus L of I. If I found out the decibel belonging to this intensity and the decibels belonging to this intensity, if I subtracted the two, that would be by how much the decibels went up. Does that make sense? Okay, so now I'm going to replace this, using this up here, I'm going to replace it with 10 log, not I, because these match, it'll be 2I over 12, 10 to the negative 12, minus 10 log I over 10 to the negative 12. You see the replacements? Now watch this. This is where what you learned today can be very useful. This one right here is the same thing as 10 parenthesis log 2 plus log I minus log 10 to the negative 12. If you expand that, the 10 belongs to the entire log, so the 10's held outside here. But I took the log, I'm looking at just this, it's the log of 2 plus the log of I divided by the log of 10 to the negative 12, which is minus. Turned into a subtraction when you expand it. Are you with me? Minus, and I wish I could string this all out in one thing, but I haven't got room on this board. Minus, and this will be 10 log I minus log 10 to the negative 12. Do you agree? You see the expansion? Now watch what happens when we string all this out. I'm going to distribute this 10 through here, and I'm going to distribute that negative, I should put it here, that negative 10 through here, and see what we got. It's going to be 10 log 2 plus 10 log I minus 10 log 10 to the negative 12. I know this is getting ugly. Minus 10 log I plus log 10 to the negative 12. Can you see that? The distribution of the tens? Now look what happens. Something beautiful happens here. Look, we got a 10 log I and a negative 10 log I. Amazing. We have a negative 10 log 10 to the negative 12. We got a positive. Oh, this was supposed to be a 10. Sorry, I forgot to distribute my 10. Sorry about that. We good on that? Forgot the 10? They got a negative 10 log of this and a positive 10 log of the same thing. They're out. What am I left with? 10 log 2. An easy thing to evaluate. Do it. That's all that's left. 10 log 2 should be an easy thing for you to punch in your calculators. Is that right?
Yep.
The decibels, by doubling the intensity of sound that your ears are able to handle, by doubling the intensity of the energy, only raise the decibels. 3. So if it was originally 40 and you double the intensity, it's now 43. That's just not that much. But that's what it turns out to be. Okay, you may want to refer back to example 6 when you hit a story problem. You may want to go back and study that a little bit to try to figure out how to do it. That's what I just did for you was this, and it's very clear in there and it's much cleaner. But that's what happens. So if you need to look back at that, please do that. The assignment for those of you that are doing it on paper is, you ready? 13 to 41 odd. That's it. It's 15 problems. And the expansion and contractions are way easier than the ones we studied. So you should go through this pretty quickly. Okay. All right, there's the end of that, whoever's viewing. Bye.